I want to tell you a little bit about a new representation I've come up with for quantum wave functions in one dimension. The idea is to use a three-dimensional representation. Use the additional two dimensions in a three-dimensional representation to represent the complex number, which a quantum wave function is, in three dimensions. So let's take a look. This is the representation of the ground state wave function of an infinite square well. It looks like a sine function, except that you see it's sort of rotating in a strange way in space. That's because at each point, the wave function gets multiplied by e to the minus I omega t, where omega is about the energy of the wave function. So the complex number at that point rotates in space like a phasor. You could also look at the first excited state. It looks like this. It has 4 times the frequency because it has 4 times the energy, half the wavelength. If a particle were in a superposition state of those two wave functions, you see the ground state rotates very slowly, the first excited state very rapidly. When you superpose them, you get something like this. Now notice that when the phasors of the two wave functions are in phase, you get a big amplitude on that side of the well. But at the same moment, they're out of phase. Now we can do a tricky thing here. We can go into a frame of reference in which the ground state wave function is actually at rest. So we rotate with it, and then it becomes a lot easier to see what's going on. The amplitude of the wave function on the side of the well where the two phasors, the two sets of phasors from the two wave functions are in phase, is large. And on the other side of the well, it's small. And one other thing we can do, we can look at the probability density, which is the absolute magnitude of the superposition state squared, and you can see that the probability actually sloshes back and forth between the two sides of the well. Now one question is, what's the frequency of that sloshing? Well, the frequency of the sloshing is the frequency with which the phasors become in phase. Well, the frequency of the ground state is 1, say. The frequency of the excited state is 4. So it has to do with the difference of frequency, or 3. So the sloshing happens 3 times every time the ground state wave function goes around once. That has to do with the difference in frequency, or the difference in energy between the two states. Here's a situation in which a wave packet is approaching a barrier that it cannot penetrate. And notice that when you start getting left and right propagating waves adding together, you get a kind of a standing wave situation, and the thing turns around and goes back the other way. Here's a similar deal, except in this case, the barrier is penetrable, so the standing waves actually get set up inside the barrier. But on the right side of the barrier, you can see the wave packet continues. On the left side, a portion of the wave packet is reflected. Here's a case where a wave packet is embedded in a quadratic potential, like a simple harmonic oscillator. You can see that as it's moving to the left, it's picking up momentum. The wavelength is decreasing, and the phasors get close together. As it reaches the other side, the wavelength increases. You get a standing wave situation, and then it goes back the other way. It's interesting to look at the helicity of the phasors. When it's moving toward the right, the helicity goes one way, and as it turns around and moves back to the left, the helicity goes the other way. If you think about a right and left propagating wave function, e to the plus ikx, e to the minus ikx, that makes perfect sense because the ikx tells you the advance of the phase of the phasor as you move in the x direction.